So in this video, we are going to talk about the patient article, which is an unsupervised representation learning method for predicting the future of patients. So let's go over the abstract. So this paper is the main baseline for representation learning over the EHRs and representing patients per se. So the motivation is that, okay, challenging and summarizing and representing patient data is obviously a hard task, and it's worth the attention. So the contributions of this work are that this work has proposed a novel unsupervised deep learning methodology for representing electronic health records and then using these representations for performing predictions. So the model they used is a 3-layer stack of denoising autoencoders. The objective is to derive a general-purpose patient representation from electronic health record data that facilitates clinical predictive modeling. So what they want to do is that they want to take the electronic health record warehouse and learn representations for patients. So they want to associate each patient with a mathematical vector, and then they want to use that for performing efficient predictions. One drawback of this data for open research is that they were using their own exclusive data set composed of 700,000 patients from Mount Sinai data warehouse. So you can compare this with, say, Mimic, in which we have like 45,000 patients, or EICU, in which we have somewhere about 200,000 patients. So go over the experimental details, and going over the experiment details is important because if someone wants to essentially build some similar approach for other databases of electronic health records, this might be shown to be important. So they had like somewhere about 76,000 test patients and 78 diseases, and the results showed that they outperformed all the base methodologies. So we will talk about this a little bit later, but they were considering the baseline methodologies as PCA, ICA, and Gaussian mixture models to kind of show that their model learns more useful and general representations. So their experiments have shown that performance on severe diabetes, schizophrenia, and various types of cancers are among the top performing. So these are things that are worth reading. So if somebody has this sort of electronic health record representation, it might be worthwhile to go over them and kind of figure out why some diseases are top performing. So let's go over the introduction. First, we want to talk about what precision medicine is. So in the precision medicine, the primary goal is to develop quantitative methods and models for patients that can be used to predict health status as well as to help prevent complications. So this is the definition of the precision medicine. Now, analysis have shown the use of electronic health records and drug effects and interactions, which is again useful for precision medicine. This is a good reference for that. And some other examples of the uses of EHRs is identification of type 2 diabetes, discovery of comorbidity clusters in autism spectrum disorders, and improvement in recruiting patients for clinical trials. Now, modern machine learning techniques have not been widely and reliably used in decision making in clinical domain. So one thing that this is mentioned in this paper because this paper is mainly about unsupervised methodologies, and so they basically what they're trying to say is that at the time of this paper, the unsupervised learning, which was something which was a thriving field in other areas of machine learning, such as computer vision, was not widely used for the problem of electronic health record representation. So why is EHR data challenging to represent? So many reasons could apply. Some of them are the high number of dimensions, noise, heterogeneity, sparseness, incompleteness, random errors, and systematic biases. So electronic health records are unstructured databases covering many domains. There are missing values, there are various frequencies of sampling, etc. All of these are actually important and play roles in making it a challenging and cumbersome task to carry out. So the same clinical phenotype can be expressed using different codes and terminologies. So this is very important. For example, assume that you want to classify a cat from a picture. the domain is clear. You're going to work with intensities of the pictures. But in this case, for example, if you are trying to predict type 2 diabetes, it might manifest itself in different parts of the electronic health records. For example, you could see a laboratory result with the value of hemoglobin A1C to be greater than 7.0. On the other hand, you could see the 250 ICD-9 code, again, representation of the type 2 diabetes, or you can read the free text type 2 diabetes mellitus mentioned in the free text clinical notes. So again, it's going to be more challenging to represent them. So supervised definition of the feature space scales poorly. That's one of the things that they say. So this is a claim of this paper. In other domains, specifically NLP, it's not shown to be a very clear and robust conjecture, because there have been cases in which supervised learning, a simple supervised learning task has outperformed an unsupervised learning task. So it depends on what type of supervision that one is talking about. So deep patient, their work is domain free, which means that they want to learn representations based on the reconstructive powers. So they don't want to bind these representations to specific tasks in order to make them general enough. And then they use these representations to predict patient future diseases, and that is the main way of showing the transfer learning capability in this case. So the EHRs are extracted from the clinical data warehouse they have. They pre-process and identify and normalize clinically relevant phenotypes and group and patient records. So they do some sort of pre-processing in the beginning, and we'll talk about some of them. So each patient can be described with just a single vector or by a sequence of vectors computed in predefined temporal windows. So each patient is then represented using these features and deep representation. So if you want to talk about this visually, we can have the data set here, they have the patients here, and then they have different data sources like lab tests, procedures, diagnosis, medications. They have the unsupervised deep feature learning, and then they use these representations for various tasks. And what they do is that for each patient representation, they have a multi-layer neural network in a deep learning architecture. So this model is what they call deep patient pipeline. And each layer of the network is trying to produce a higher level representation of the observed patterns. So this is again the same as almost all the convolutional neural network based methodologies in computer vision, for example. So again, we're trying to kind of do some sort of a bottom-up reasoning. So they do some sort of a late fusion, one would say, because this is again from this. We want to kind of hierarchically combine lower level features to unify them, so you don't want to combine all of them in the beginning, so we don't want to do an early fusion. And let's see what these noisy legato encoders are. So imagine that we have the x's as inputs, we have the d-dimensional values between 0 to 1 continuously distributed. So we have this encoder function f parameterized with a set of parameters theta, and it takes the x, so it performs some sort of affine transformation, and then it passes it through the activation layer and nonlinear activation layer and generates latent representation y for us. And then y would be the auxiliary representation, and then the reconstruction could take place with the decoder g parameterized by theta prime, and it will generate a reconstructed version for us. So the weights for the decoders and encoders are tied. The code is y is distributed in a way that captures the coordinates along the main factors of variation in the data, and they have different objective functions for this. The idea here is that first we can take the x, which is the original input, and then they do some sort of corruption on it, so they have this noisy x again. So this is formally used in autoencoders because it will help with generating robust representations. And this representation will be used to generate a reconstructed version of the input, and z is going to be compared with the original x, not the noisy one. To kind of corrupt the x, what they do is that they mask the data. So this is similar to what they do in training BERT for word representation learning. So one thing that has been shown in the literature and various papers is that methodologies relying on masking usually work well, but There usually are, so this is kind of an underuse of the capacity of the network. It has been shown in many cases that masking causes the train distribution to be different in test, therefore causing the model not to use the full capacity of the data set. The loss function that they have is this, and they train the model using the mini-batch stochastic gradient descent. And for the evaluation, they've been using their own Mount Sinai dataset. So it's important to know the number of records in this case and the periods. So they have 12 years of data possibly. They have the data from 1980 to 2014 of ICD-9 codes, which is 34 years, and it's a lot. They have 4.2 million de-identified patients as of March 2015. So the bottom line is that the data set is huge. They use the Open Biomedical Annotator, which is a RESTful API data application that basically is going to be able to associate codes, SNOMED, CT, UMLS, and RxNorm to free text. So they use these in representations as well. They try to identify the negated tags and remove them using these approaches here. And then they basically parse the nodes further and perform unsupervised topic modeling. Namely, they use the latent Dirichlet allocation and obtain topics for the models for patients, and they realize that the 300 number for topics is a good number of topics. And again, they do average something similar to dynamic averaging networks in order to kind of do average pooling over the representations. So these are more specifications regarding the split of the data. They apply the SDAs, 500 hidden units, and 5% of the data will be masked. For the baselines, they compare with PCA, K-means, Gaussian mixture model, and ICA. And for the deep patient model that they have, they first do an L and then find the good hyperparameter sets. And then for the task to test the learned representations, they use the future disease predictions. So this disease classification results specific. So accuracy indicates the skewedness of the data set, which is something common in the EHR data sets. F1 scores shows that this is a very hard task in general, especially since the ROC-OC is not over 90%. Some of the top diseases are these. So again, this is important to kind of go over the diseases and see why these are top performing and why are some other diseases bottom performing. Maybe there are not enough data, maybe there are some similarities. This is something that falls in the category of data science mostly. And they show again that deep patient is the superior methodology of the baselines. So the future work on this case would be on trying to learn better representations. But generally this paper is the foundation of patient representations, one would say.